Okay, welcome back everyone. So today we're going to take a look at some variation of something called Abel's theorem. And the reason being is that, in a previous video we discussed the divergence of the harmonic series. Today we're actually going to look at sort of a different approach to proving its divergence, but in a sort of more overkill way with this big theorem. Though it's quite easy to prove, so it's not that overkill, but it is sort of a detour around what we did in a previous video. So I just wanted to show that today, and it's an interesting theorem. So let's take a look at it. So let's say we're given a sequence that satisfies the following two properties. It's positive. That is, in this case, all of its terms are greater than or equal to 0. And also it's decreasing, meaning given some term in the sequence, the next term is larger than that term, or the next term is smaller than the previous term. Okay, that's the notion of decreasing. Okay, just get my marker to work. Seems to be a recurring problem. Okay, so let's see how to start here. Maybe for the proof, it would be useful to first outline, perhaps, what we're given. So, suppose a sub n is a sequence with the given properties. Okay. Okay. And let's let S sub n denote this partial sum here, partial sum of this infinite series. So Sn equals k from k equals 1 to n of a sub k in this case, right? In fact, this should be a sub k definition. That was a bit of a typo. This looks like an n. That's the problem with my k's, but just note that these are all k's. Okay, and this is an n, of course, because I'm crazy. Okay. So let's see. Well, let's perhaps, given this notation, let's kind of analyze another sequence. And to motivate that, well, we don't really know directly what the limit of this sequence is, because I mean we know it converges by assumption, right? But we would have to give some arbitrary, like a letter L, to what it converges to, and that's not really that helpful. So, but for now, let's start with that, then we'll get to something better. So as n tends to infinity, let's say this tends to L. Okay, then now let's get to that part where we analyze another series which will get us closer to this goal. Okay, so let's see. So okay, so let's consider the following sum, which is the sum from k equals n to 2n, okay, of a sub k. And indeed, we should be able to write this in terms of some s something, s sub something, right? So let's try that. Well, consider the sum from k equals 1 to 2n of a sub k. Well, we're subtracting off some terms, and in fact those terms are just the terms from 1 to n minus 1. So in other words, this is just, I'll write it out fully to make it clear. K equals 1 to 2n of a sub k minus these first few terms, k equals 1 to n minus 1 of a sub k. And that's just, to make it clear, s sub 2n minus s sub n minus 1. Well, these are both subsequences of our Sn, and well, it's not too hard to show that given a sequence that converges, all of its subsequences converge to the same value, L. So in this case, L. So this converges to L. This converges to L. So this, in general, just tends to 0. And that's kind of what we wanted, right? We have an explicit value for what it tends to. And furthermore, we can kind of start reaching this limiting idea here. And to do that, maybe let's start using some of our tools here, our givens, right? Well, first of all, that it's always greater than or equal to 0. That's helpful because we can always bound this below by 0, bound the sum below by 0, although we're just adding up a bunch of positive or non-negative terms, so we're good there. And since it's decreasing, well, let's kind of see what we can do there. So again, analyzing the sum, which again tends to 0, we have the following. Let's see. So maybe let's write out some terms. So let's write out some terms. I'll just use equals here. By assumption, we're saying all of this stuff equals, let's say, a sub n plus a sub n plus 1 plus dot 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 plus a sub 2n. Okay? But now let's see. So what we want to do is, well, we want to bound this below by something. And since and then we'll use the squeeze theorem, but let me make that more explicit. If we bound this below by something that's non-negative, well, first that thing is going to be bounded below by 0, of course, but now it's bounded above by something that tends to 0. So by the squeeze theorem, that will tend to 0 as well, and we'll be able to use that to get closer to this. And indeed, using the fact that it's decreasing, we note that, well, this 2n term is going to be, well, less than everything here. So to write that, so using decreasing fact, I'll abbreviate that, for all k less than 2n, a sub 2n is less than or equal to a sub k. Okay, so that k ranges from, in this case, we just have to worry about from n to 2n minus 1. Okay, nice. So what does that mean? Well, that means if we replace all of these terms by this a sub 2k, by this a sub 2n, well, then we're going to have a lower bound for this, right? Since every term is less than that. So this is going to be greater than or equal to the following. Well, how many terms are there? Well, there's actually, if we start from 0, we go to, well, this is n plus n, we go to n. There's n plus 1 terms. That's not ideal. So maybe let's first get rid of one of the terms. Well, we can just get rid of a sub n. So let's just do that. Let's get rid of a sub n. If we take away a sub n, it's just a positive term. We can take it away. Then this is, of course, greater than this sum a sub n. This is kind of ugly. So this is greater than or equal to a sub n plus 1 plus dot 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 plus a sub 2n. And now, well, we have n terms, and using the same logic, this is going to be greater than or equal to, there's 2n terms, 2n times a sub 2n. There's 2n of, we're counting up 2n of these a sub 2n terms. Okay. And, well, this is bounded below by 0, and since this tends to 0 by our argument, well, more specifically, since this tends to 0, this has to tend to 0, so this also has to tend to 0, okay? Or, I mean, it suffices to just use this, okay? Well, then we've come quite close to our result, but these are just the even terms, right? So we kind of want to do a bit more. We want to look at most of the odd terms, and I say most for a reason, and we'll look at that in a second. But let's take a look at the odd terms. So if we have, so odd, so if we have two n plus 1, a sub 2n plus 1. That's what we want to work towards. Well, since we're decreasing, this is going to be strictly less than the previous term, right? Since by assumption we're decreasing, so that this term is going to be less than the previous term in the sequence. So this is less than 2n plus 1 times a sub 2n, okay? But maybe just using some algebra, we can multiply and divide by some value, and we'll use 2n. So we have 2n plus 1 over 2n times this 2n times a sub 2n. The reason we're doing that is look how nice this is. We have a 2n times a sub 2n, and what do you know? This tends to 0. In other words, we have some scalar multiplying. We have something that remains constant multiplying something that tends to 0. Or I guess actually this is important. We can't just leave this off. So we're looking at the product of two convergent sequences. This sequence was 2n plus 1 over 2n. We can rewrite that differently by kind of distributing that 2n. So 1 plus 1 over 2n, I believe, yes. And well, indeed, if this actually diverges, then we might have a problem, because even though this converges to 0, this diverges, so we'll have some indeterminate form going on there. So as n tends to 0, as n tends to infinity, this converges, so indeed this entire thing will tend to 0. Okay? And so what do we have here? Again, this is always bounded below by 0. By the squeeze theorem, this middle thing will have to tend to 0. Okay, so what have we done? Well, we've looked at most of the odd terms and all of the even terms and concluded that both of those are going to tend to 0. So the entire sequence should tend to 0. And now coming back to what I said with that most, using the word most, well, notice that this is 2n plus 1 and not 2n minus 1. So we're actually missing the n equals 1 term. 1 is odd. So a sub 1 is an odd term in the sequence. Right? But we don't really need to worry about that because that's just a finite number of terms. One term is a finite number of terms. So in general, that won't change the limit of our result, right? If we take off a finite number of terms, it's not too hard to show that that won't change the limit of a sequence. So indeed, we have concluded this proof. So I'll just denote that by a little box. Q, D, D. Maybe to address what we talked about with the harmonic series, well, it's super easy. So notice that if we have a sub n equals 1 over n for n a natural number, so this is our sequence, n times a sub n equals 1, and this does not tend to 0 as n tends to infinity. Namely, if we take the contrapositive of this, this sequence doesn't converge, namely diverges, so the harmonic series diverges. So that's a quick way to show that the harmonic series diverges, given that we have access to this theorem. So I hope you enjoyed this video, and I'll see you in the next video where we'll most likely continue with real analysis. See you then.